Okay, so we're continuing from where we ended last time. Still discussing the flywheel. But this time around, we want to look at the coefficient. Talking about the coefficient of fluctuation of energy for a flywheel. But then we also need to be careful because it's also looking like we're just dealing with the same formula, but it's the way we are using it that makes the whole application slightly varied. In the initial case, we said the fluctuation is given by the difference between the maximum and the minimum energy. E1 representing the maximum, E2 representing the minimum. Now with this, you can still go ahead and plug back the original equations where we said this is supposed to be half I omega squared. And this is 1 minus half I omega squared, and that's number 2. When factorized, the equation turns to this: half I outside the brackets. Then inside the brackets, you have omega 1 squared minus omega 2 squared. Now, the last part, omega 1 squared minus omega 2 squared, in mathematics, this is the one you remember where you talked about the difference of two squares. You can expand it or factorize it as it has been done below here, where you just ignore the square, remove the square, but you now introduce W1, or rather omega 1 minus omega 2. The other one will have a plus, the first one has a minus. Then you've expanded it using the difference of two squares principle. Looking at this one, you will notice that we can combine half and the last part, which is this one here, omega 1 plus omega 2 times half, or everything over 2. It gives you what is below here, which is the mean velocity. Meaning that we can simplify this equation further by substituting where there is omega 1 plus omega 2, including half, we just put omega. With that, you can now introduce one factor which won't change anything, which is omega divided by omega. Multiply it by this expression. What will happen is that for the first part, the omega will multiply by this other one, which is out here. Then you have omega squared. Then the other one will go inside and give us this fraction here. While we're looking for this, it's just to come up with the first one, which is CS, the coefficient of fluctuation of speed. And that one will be very useful as we go, because that gives us some factor to help us how the energy is fluctuating. Also remembering that the moment of inertia is given by mk squared, combining with that. Then when you bring CS and I, or rather moment of inertia, substitute them in the original equation for fluctuation in energy, you find it becomes, where there was I, we have mk squared, the W squared is still there. The last part now becomes CS. The last part simply becomes Z. CS, or the coefficient of fluctuation of speed. You want to go back to this part if you're required now to look at how did you arrive at the formula. You want to do some analysis, that's where you do this. Otherwise, this is the part where you only focus mostly on the formula that you are going to use. Now let's see how this can be applied. Here's the question. It says the turning moment diagram for a petrol engine is drawn to the following scales. Turning moment, where the 1 millimeter representing 5 Newton meters, the crank angle 1 millimeter representing a degree, or rather 1 degree, The turning moment repeats itself every half revolution of the engine, and the areas above and below the mean turning moment line taken in order are 295, 685, 40, 340, 960 to 70, and everything in square millimeters. The rotating parts are equivalent to a mass of 36 kg. So this is already giving us the mass at a radius of 150 millimeters. Calculate the coefficient of fluctuation of speed when the engine is running at, or rather runs at 1,800 RPM. Now, from here, we can now plot down the data. Some important factors are, we have the 1 millimeter representing the torque, or rather that turning moment. Again, the same millimeter representing the turning angle. Then what we have after that is a scale. Now in the scale, we want the area. The area requires that you multiply this by that to get a square meter. Multiply the two. So that 1 square meter should be able to represent a particular value that we'll be looking for. So in this case, we have 1 times 1 gives us 1 square millimeter. So you also multiply that 5 by this other angle converted to radians. So 1 by pi over 180 multiplied by 5. When you simplify this, you get pi over 36. Again, the radius of gyration has also been given, 100 millimeters. You don't leave it in millimeters, you convert it to meters, so it becomes 0.15. Then the mass, everything is 36 kg. Then after that, we need the mean speed. The mean speed is 2 pi times 1,800 over 60. When you convert this, you get 188.496 radians per second. Now, we go back to the question, you realize the numbers were given above and below, above and below. So here, I can still go ahead and look at those just to confirm, but otherwise they are just here. 295, 685, 40, 340, 960, 270. So above 295, below 685, 40, just like that. So it's starting with the positive, negative, positive. Whatever is above is positive, and what is below is negative. Just like that. Now, having done that, we can now interpret this one because we already have those negatives and positives. So when you're drawing, you don't need to stress because the bigger the number, it will require that you also capture a bigger catchment there, including even the height here. But the total area which is bounded here is the one that we're interested in. That area, that one is the one we want to keep. These numbers not all of them can fit in those boxes. So hence, they are being shown like that. Now, at the start of the cycle, you're starting with the total energy, which is E. Then after that, you continue dealing with what is there. So at point A, you have E. Then you continue, there's E, you go to point B. Point B leaves behind 295. So you're going to add E and the 295, which is positive. Moving on, when you go to C, you will find you have left 685 and 295. So you add them, 295. But remember, 685 is below, which makes it negative. So it's E plus 295 minus 685. End result is E minus 390. If you go now to D, 40 joins the party. So now what you have is E plus 295 minus 685 plus 40, because the 40 is above, so it's positive. And your answer, E minus 350. Again, if you go to E, we're starting again. The energy we started with is total energy E plus 295, 685, 40. We include the one below, which is 340, negative 340. And the end result is E minus 690. Then moving to F, you have E plus 295 minus 685, 40, 340. The newcomer here is this one, 960. And if you check, our 960 is positive because it's above. So added, if you want, you can even just include it to the last one there, and it will still give you the same result. So this becomes E plus 270. When you get to G, you add everything, including the last one, which is 70, as below. So take away 270 rather. The end result will be a 0. So it will be like E plus 0. Then we have E as our final answer. If you look at E, it means we're just starting the cycle back to A. Again, the whole scenario will repeat itself. So meaning the analysis that we get applies to this performance. So here we have the answer that we're looking for. Now, what we need to do is to calculate the change in energy or the fluctuation of energy. This is maximum minus minimum energy. So the change is equal to, the maximum value is E plus 295. The minimum, if you check, which is the biggest negative, which makes it a minimum, because with negatives, the bigger it looks, the absolute bigger number it looks, the smaller it is. So in this case, 690 happens to be the smallest. Then in the positive side, there is 295 and 270, which automatically means we pick E plus 295. And there, then we have E plus 295, take away E minus 690. Then after that, we can just do the simplification. There is E minus E, which will cancel. Then those two can add. So we have 985. But the problem we can see here is the unit is wrong. Why should we be using square millimeters when we're talking about energy? Let's convert. What we have here is pi over 36 was the one representing 1 joule. Pi over 36. So 1 square millimeter was representing this amount of energy. So to get rid of that, to make sure that we can have now the energy correctly done, because this was like saying joule per square millimeter. Because in the end, we said 1 square millimeter was what we had. So then what happens? The square millimeter will cancel with the 985 square millimeters. Then when you multiply those, you get 85.957 joules. Now that we found this, we can now go back to the master formula. In the master formula, that's where we say change in energy is equal to mk squared w squared and cs. So all we do now is just substitute. Change in energy is 85.5957. The mass is 36 kg. Radius of gyration was given as 150 millimeters, which turns out to be 0.15. Mean angular velocity, 188.496. We also square it. Then we make CS the subject of the formula. Of course, I have to emphasize here that the way you go about your algebra may not matter, but just make sure that you show every step. Show every step where you can multiply the 36 by 0.15, multiply it also by 188.496, get one number there. Then that number is multiplying by CS, so divide it on both sides of the equal sign. And then you find your CS becoming 0.00288. Depending on how you moved around with your values, this can easily become C and, okay, let me just do this. C and a small s being equal to 0.003 is the same thing. Let me just remove that one. That can easily become your CS. Now, this is our coefficient of fluctuation of speed. And whenever you're calculating for it, sometimes you may find that you've been given, or the question requires you first of all to calculate for it using that other formula we had used in the past, or the formula that we derived. It's the same formula. Then you may find perhaps you need to determine what the mass is. So you make M the subject, and then you proceed from there. Otherwise, it is as simple as that. After that, here's the exercise with only 4 questions. Question 1 and question 4 are basically refreshing you on what we've just talked about. The others, question 2 and question 3, are trying to recap on the previous lesson on the same. But both of them are referring to the energy related to the flywheel or the engine. Okay, for now, we shall end here. I will announce the next one following through.